Okay, we've been talking about how to find the shape of a graph and sketch the graph of a function using lots and lots of information. Now we're going to kind of do something that uses a little bit of that, but to answer a different kind of question. So the kind of question we're going to be asking is about optimization. That is, how do you do something in the best way? Before I get going with this example that we'll do, again, there are lots of examples in the book. They all take a while, so I'm only doing one example on the video, but I encourage you to read the other ones in the book. Okay, so we want to be dealing with a situation where there's some quantity to be minimized or maximized in order to do something in the best possible way. The quantity will be labeled Q, and usually that quantity will depend on one or more variables, like the area of something depends on the length and width, or the time something takes depends on the speed at which you go, things like that. Okay? Often the problem will also have other information in it that relates the variables to each other. We'll see an example of this a little bit later. So what you have to do is write a formula for Q, that is the quantity we're going to find the minimum or maximum of. It will have variables in it, and you use other information from the problem to get rid of all but one variable. Because we are only doing calculus of functions with one variable in this class, we need our function Q to only have one variable in it. So we need to get rid of all but one variable. We find the domain for that variable, that is, what values make sense in the context of the problem. And then we use calculus to find the maximum or minimum for our function Q on that domain. Okay, so here's an example. I have 1,200 square centimeters of material, and I need to make a box with a square base and an open top. What can I do to make the largest possible volume for the box? So I have a certain amount of material, I want to make a box, square base, open top, and I want the box to hold as much stuff as possible, largest volume possible. Okay, since it's the largest volume I want, that means I'm looking for the maximum of something, the maximum volume. And that volume, the thing I want the maximum of, is Q, our quantity to maximize. So Q is the volume of the box. Okay, so here's a picture. Here's my box. It's an open-lidded box. It's got a height, a width, and a length. But the problem says the box should have a square base, so that means the width should equal the length. So I'll erase L and put in a W. Okay, Q, again, is the volume of the box, which is height times width times, again, width, HW squared. So there's our formula for Q. It's got two variables. We only know how to do calculus with one variable in a function, only to find the maximum or minimum, so we need to get rid of one of those variables. Well, how can we do that? We use the other information in the problem. In this case, we haven't yet dealt with the fact that we have a limited amount of material. The other information in the problem is we have 1,200 square centimeters of material available. That's an area, so our other information comes in the form of an area. Well, how much area, or how much of the material, is going to be used in our box when we make this thing? Well, the base uses W squared area, and each side is an H by W rectangle, so the sides area are each HW, and there are 4 of them. So the total area, the total material used, is W squared, the base, plus 4 times HW for the sides. Remember, there's no top on the box. So our 1,200 square centimeters of material have to be enough to cover W squared plus 4HW, and that relates W and H. So that we have 1,200 is got to equal W squared plus 4HW. So here's the situation. We want to maximize the function Q equals HW squared, and we know W squared plus 4HW equals 1,200. I can solve that equation. It's easiest to solve it for H. If I solved it for W, I'd have to use the quadratic formula, and nobody wants to do that. So I'll solve it for H and get 1,200 minus W squared over 4W. And I can substitute that into Q. So Q is now HW squared, and it's written like that. simplifies to 300w minus w cubed over 4. That's the function I want to maximize. What's the domain? That is, what values of the variable w make sense in this problem? Well, w is the width of the base of our box. So first of all, it has to be a positive length, right? You can't have negative or 0 for the width of your box. So it needs to be positive, above 0. And the biggest it could be would be the biggest I could make the square base given the constraints on material. Well, I have 1200 square centimeters of material, so I need that base to be area 1200 or smaller. And so the square root of 1200 is the biggest. In fact, I can't quite get to the square root of 1200 because I need a little bit left over for the height of the box. I don't want to make just a flat square. So up to but not quite equal to the square root of 1200 is w, and anything positive up to that amount. So there's the domain. So I want to maximize the function 300w minus w cubed over 4 on the interval from 0 to 1200. Sorry, 0 to the square root of 1200. Okay, how do we find maximums or minimums? We look for critical numbers. Then, if we had a closed interval, we could do the closed interval method, but we don't, so we're going to check the shape of our graph. Critical numbers mean find the derivative, which is there, and look for places where the derivative equals 0 or the derivative does not exist. If q prime equals 0, that means 300 minus 3/4 w squared equals 0. And you can solve that and get w equals plus or minus 20. But since I'm only working on the domain from 0 to the square root of 1200, w equals 20 is the only one of those in the domain. All right. Q prime does not exist, on the other hand, never happens in this case, because q prime is a polynomial, and polynomials always exist. Okay, so here's our q prime number line. The critical number is 20, that's the only one, and here I'm going to mark the beginning and end of my domain, 0 to the square root of 1200. So I have two intervals to check. Check in the first one, if w is a number between 0 and 20, then q prime is 300 minus 3/4 that squared. So for example, w could be 1. That's clearly positive. On the other hand, if w is bigger than 20, I get a negative value for q prime. Like for example, if w is 40. Well, 40 is too big. Anyway, 22. You can plug that in. You get a negative number for q prime. Okay, so what does that mean for the shape of our graph? That means between 0 and 20, the q prime is positive, so the function q is increasing. And then after 20, q prime is negative, so the function is decreasing. So it looks like this, increasing, then decreasing, and there's that local maximum at 20. But because that's all that happens on our domain, that local maximum is actually a global maximum, an absolute maximum. Because there's no other up and down. It just goes up to that point and then down. That actually is the highest point. We can see that from the shape of the graph. So we wanted the maximum of the function, and we have found that the maximum value of the function q will happen when w equals 20. So what is the maximum? Well, we plug w equals 20 into our formula for q. Q equals 6,000 minus 8,000 over 4, which is 4,000. And I need some units on that. Q equals 4,000 what's? Well, Q is a volume, and in this problem measurements are in centimeters, so the volume will be in cubic centimeters. So Q is 4,000 cubic centimeters. Okay, so the answer to the question is the biggest volume box I can make has a volume of 4,000 cubic centimeters. Now, the question didn't ask this, but we can also give the dimensions of the box that will produce that maximum volume, because we know the base is w by w, and we know w is 20 centimeters by 20 centimeters. What's the height of the box? Well, we have a formula for height. Plug in w equals 20, and we get 10. So the height is 10 centimeters. So our box will be 20 by 20 base and 10 centimeters high, and that gives the maximum possible volume for our box, 4,000 cubic centimeters, given the constraint that we only have 1,200 square centimeters of material to use. Okay, so there's our answer. The maximum possible volume is 4,000 centimeters cubed. So what did we do? We figured out a formula for the thing we wanted to maximize. It had two variables, so we had to use other information to get another equation involving those variables, solve for one, and then substitute it back into Q to get Q in terms of just one variable. We found the domain we were dealing with, and then we used calculus, found critical numbers, and looked at the shape of the graph to see where the maximum point was on the graph. The video question is, in this problem, why was the domain what I said it was? So just a sentence or two explain why the domain is that. And I do again encourage you to read more examples in the book. They take a while to do, so we won't be able to do that many examples in class, but I hope you can read them and see some more examples. All right? I will see you in class. Bring the video question.